Okay, hello, good evening. Of course, I'm a little bit, yes, a little. I'm here. I'm here because I just finished the other session. Hello. Yeah, you can hear me. I can see this. Yes, thank you for joining me. I know that it's late, but we can do that really nice and how do you say, short and sweet. Sweet and short, I don't know. It's quite short session, maybe. We will see. Unless we, short and sweet. Thank you, Heather, yes. That's how you can, yeah. Okay, that's me. No more talking, let's start. That's me what we have. We do have another application of the integration, like we know how to find the areas. Now we will try to find the volume of something that has fancy shape. Okay, not like a nice like cylinders. No, something like, I think I mentioned yesterday, something like loaf of bread, for example. Yeah, and again, not the square like a nice sand square. No, like a proper bread. Okay, that's what I have. Volumes. But first of all, let's start with something that is theoretically easy. That I hope we do have some intuitive idea how to compute the volume. Okay, and the easiest way is to check taking a cylinder. Okay, cylinder, you probably, when I will say cylinder, you're probably thinking about the circular one, yeah, right away, like that. That's what we. But the definition of the right cylinder is actually that we may have any shape, okay, and I can have this shape in the bottom and the top base. They have to be, could be any shape, but both of the bases, they have to be identical, which we call congruent, and they have to be parallel. And we can see, this is like a little bit different shape. This one is a rectangle, this one is a square, but bottom and the top is the same. And when we connect the sides from the top and the bottom, they always have to be perpendicular, right angle, okay? Between, like a right angle between the base, let's say the floor and the sides, okay? That's actually cylinder, congruent bases and perpendicular sides, okay? And now, having this shape, okay, solid, okay, to find the volume, we will just compute the area of the base times the height. Yeah, that means when you are like doing some engineering project or something, you have to find the volume. And when you realize, oh, it's a cylinder, then just the area of the base and the height. Yeah? And for example, pi r squared times h, because at the base is just a circle. Okay, that means the area of the base times the height. The area of the base, which is length times width, times the height. Of course, that's the box. This one is a little bit weird. I don't know, half of the circle, or maybe kind of like an ellipse. Hyperbola. But still, I can find the area of the base and times the height. Okay, that's not a problem. The heights are perpendicular, nice and straight. Okay, yeah, that's the reason that I can use this formula. But now, the point is, because we will have, of course, a little bit more complicated problems. Let's take something like this. Please look at the blue shape for now. Okay, looks like, I don't know, probably like, maybe like football. I took the picture from your section, from the textbook. Okay, that means the point for us is to find the volume of something like that. Okay, which, yeah, we can see we don't have, if I will look at this, theoretically, I do have one base and another base. If I will take this like in the vertical position, it's kind of like a cylinder, but this is the curve. The sides are not perpendicular. Yeah, that means I can't really use right away my formula the area of the base times the height. Now, that means what we will do. We will try, okay, we will try like to, now actually is good moment that you may imagine this as a loaf of bread, which I'm like repeating this, and imagine that we slicing the bread, okay, and we do have like a curve on the top, but when you take the slice, and if the slice or slice of bread, slice of bread, when it's relatively thin, yeah, and if I will put like on my plate, it looks like a cylinder, yeah, because we do have the same base, the top and the bottom, and the height, of course, the thickness of the slice, like this one, yeah, we will call delta x. This looks like a one slice. That's when I put on the plate, it's my height. And if it's tiny, even if it's a little bit rounded, I can still approximate and find the volume of that slice. Do you think makes sense so far? Like finding, yes, okay. Like finding the volume of one slice of the bread. Okay, that means I can find the area of the base. We will find the area, and then just the thickness, just the height. Okay, that means that's what we will do. We will cut, and actually I can find the volume of one slice, but adding all of my slices, the volume of all of the slices, I can have the volume of my bread. Okay, that means that, and if I have infinitely many of these slices, then I will approximate perfectly the curve on the top. Yeah, we know this idea, yes, slicing and adding together. Of course, you may probably think that integration is involved. Okay, that means this is, again, some my comments, my notes. Finally, I have my slicing the loaf of bread. Okay, that means, again, looking at this, the delta x will be the thickness, okay, or the height. But this pink, yeah, when I will take the a of x, will be the we will call like cross-sectional area, because we have to take like a plane, or we can think about knife. We can take a knife and we can cut perpendicular. Okay, we cutting perpendicular to the cutting board. Okay, that's when we're slicing the cutting board. We're slicing the x-axis. Okay, because that will be important. We will integrate the x-axis with respect to x. Okay, let's look at more slice. That's a little bit better. Okay, that's of course, that's too thick. Yeah, that we have 1, 2, 3, 4, 5, 6, 7. That's not a good approximation. But as I said, when we will cut a little bit, like, I mean, really, really thin slices, we will perfectly approximate, yeah, the line. Okay, that means just one of the slice, one of the slab will have the base area we will call a of x, of course the sample point like x sub I, and the height, which is the thickness delta x. That means this is the volume, the area, the base area times the height, the area of the base times the height. This is just one cylinder. Now, adding the sigma, I am adding all of them, because sigma means addition. Okay, that means I am adding all of them. And we know that n is a number of the slice, and if n is huge, then it's perfect approximation. And of course, huge, that's my notation for huge. Okay, limit as n goes to the infinity of the sum of, and this is base times the height, which is volume. Okay? That means I am adding infinitely many of these slices. That's my approximation. That means that's simply the formula for the volume of the different, like, irregular solid. And this will be the formula. That means I know that some of you are taking notes. I can see this. Okay, but I can give you the final formula because, you know, I always want to introduce the theoretical part, but then I'm giving you nice formula and we can, yeah. And I will just repeat, limit of the sum, of course, is the integral. That's, let's look at this. Limit of the sum, or I can say adding infinitely many terms means integration. And this will be the cross-sectional area. And since we like slicing or we dividing, we cutting the x-axis, we integrating with respect to x. Okay, that means the only thing that we have to remember from this section, in order to find the volume of the solid, we have to integrate the cross-sectional area with respect to x if we cutting the x-axis, because we may have the solid which will be like placed along the y-axis, then we will cut the y-axis, then everything will be in terms of y. Okay, but we will have relatively easy shapes. I mean, still not cylinders, but relatively easy with respect to this cross-sectional area. Yeah, we will be able to find easily. Okay, that means let's see, because we will only focus of the solids of the revolution. We will rotate something. That means okay, for example, this one. This is the first, it should be example 1. Find the volume of the solid obtained by rotating about the x-axis from 0 to 1, the region under the curve square root of x. Okay, that means now we have to imagine something. We have a function square root of x, okay, and from 0 to 1. Yeah? Like, be of course above the x-axis. Okay, that means that's the region. And now what I'm doing, I have to kind of like take this blue part and like swipe around the x-axis. Okay, like you can probably imagine that we will get something like that. Yeah, please ignore the pink. I mean, we will look at the pink. Of course, you know what pink means, the pink part. Okay, that means this is like kind of like I can't say coffee cup because we don't have like a hole, like a solid inside. Yeah, like a ball, but we can't put nothing inside because it's solid. Okay, that means in order to get the volume of this shape, we need to find the cross-sectional area and just integrate. Okay, that means what this means, I will take knife, let's say, and I will cut this, right? I will slice it, right? But now I will focus on just one slice. That means this is the one slice. It's really nice. And we know that the thickness is delta x because I'm cutting the x-axis. And now, because I will set up an integral with respect to x of the cross-sectional area. But who can tell me, almost the first question today, what will be the limits of integration? Can you tell me the limits of integration? Like, you have to always think where we starting our cutting and where we finish. The initial, yes, that means I will start from 0, okay, I will cut and I will end at 1. That means from 0 to 1, okay, because that's important. We need that limits. Yeah, that's how you can always think. Integration, slicing and adding together. And now, what do you think? The cross-sectional area, what shape we have? What shape is this? The pink disc, I can say. It's a circle, yeah? Of course, it's a disc, but yeah. That means just simply, do you remember the formula for the area of the circle? Pi r squared, of course, great. Okay, that means this is disc because it's solid. Then pi r squared. That's what we have to do. And Okay, pi r squared, but now we have to think how the r, the radius, is defined. Okay, that means this is radius of that, yeah? It's a disk, it's a circle, but what is the radius? We need the radius. Radius is the value of the function, exactly. Because when I'm picking my x like sample point between 0 and 1, the limits of integration is taking care of that x. That means the x is somewhere here, okay? And I need this length, this distance, and this is simply the corresponding y, and the y is defined as a square root of x. That means this will be my radius because I need in terms of x. Like if this will be, I don't know, 1/2, the height of this radius of this distance will be square root of 1/2 because that's how function is defined. If this will be, I don't know, 1/4, it will be square root of 1/4. Okay, that means radius is simply, I just type for you, it's a y value, but the y value is defined as a square root of x. Okay, that means that's almost nothing. That's the most challenging thing, to identify the cross-sectional area. And of course, square root of x squared is x, and the volume is just the integral. That means we simply integrating pi x. Okay, I think I can give you a minute. Do you think you can give me the final answer? What's the integral of x? And evaluate from 0 to 1 and multiply by pi. Oh, okay, we do have, of course. We have, you can, yeah, everybody can type. I will not tell you if this is correct. Yeah, let's wait for more students. We know integral of x is, okay, we have Heather, pi over 2. We have Joshua, we have Abdallah, we have, oh, I see, I don't know if it's, yeah, okay, Anthony, Kieran, I don't know if I'm pronouncing, of course I will never know how to pronounce, I can, yeah. It's so nice that you have the camera on, I like it. Brooke, Anthony, Andrew, okay, Remy, okay, yeah, I think, let's see what I typed. Oh, did I copy twice my integral? I don't know why. Yes, it's just x squared over 2, 1 over 2, and 0 will be, yeah. Okay. Yeah, that's what you can see. That's, yeah, that's it. But no, let's solve more problems. Let's take another function and let's rotate. Okay, now let's find the volume of the solid obtained by rotating the region bounded by x cubed, and then y equals to 8, and x equals to 0. And now we do have a rotation about the y-axis. That means we have to take, do I have, okay, I have the graph, but okay, I can show you, I think. Yeah, we can see blue curve is the x cube. Horizontal line is y equals to 8. And x equals to 0, it's simply the y-axis. Okay, that means that's the blue region bounded by all of the curves. And now what we have to do, we have to take this blue part and do the same thing, but around the y-axis. Okay, we will have the same, almost the same thing. We have to like rotate about the y, and looks like that. Okay, that means now I will ask you first, we will integrate in terms of x or in terms of y? In terms of y, because we will take, like, we have this solid, we need one slice. That means I will start slicing this way. Yeah, that means that's how you can always think. Whichever axis you're slicing, this means we're integrating with respect to that variable. Okay, what will be the limits? What are the limits of integration? Yes, okay. The limits are because we from 0 to 8. Perfect. Yeah, okay, you understand. Okay, that means we will, I think I typed the answer, but I will show you later. Okay, that's we definitely know that we will integrate with respect to y from 0 to 8. Perfect. But now the cross-sectional area. It's still a circle, pi r squared. But now we have to find the radius in terms of y, because since we're integrating in terms of y, we're rotating in terms of y, everything is in terms of y. We have to define that radius in terms of y. That means, let's see, I have too much. That means that's radius. Okay, that means radius, of course, it's defined, it's actually the distance from the x-axis. That means I can say the radius is like x. Okay, but we're not satisfied with x because we want the y formula. That's mean what we have to do. I can even write here. Okay, that's my x, that's the radius, but it's actually touching a function. Okay, that means I have to take my function, which actually I did here. Okay. Because how can we can even like numerically, we can even think numerically, then it will be easier. Like let's say because I'm integrating between 0 and 8. And let's say I will pick the value, I don't know, 5. That means if this is 5, if the y is 5, what is the corresponding x value? How can I compute this? My function is defined as a, yes, function defined as a x cube. That means if this is 5, how can I can just take the cube root. That means then I can find this. That means this will be cube root of 5. That means if this is like just y, okay, like just y, I can just compute x and I will have cube root of y. Okay, I will erase this because it's a little bit too much. Okay, that means if this is y, this is x, but x, of course, is defined as a cube root of y. That means this will be cube root of y. That's the radius. We're squaring the radius, and we do have the formula for the cross section part. Okay. Yeah, that means, do we understand? Because we took the equation and we simply have to solve it for x. Thank you. Because we're solving for x because we need the y formula. We will solve for y if we need the x formula. Yeah, we can always like play with the given equation. Okay, let's just integrate. Oh, we don't even have to integrate. I have this, and then I have volume. Yeah, I always think that I typed everything before the session, but I sometimes writing it's better. But we have nice. As we can see, we have the radius in terms, I mean, is x, but we really need in terms of y. And we just have to integrate this. Yeah, this one is a little bit more crazy because it's y to the power of 2/3. Oh, that means the integral, the integral of y to the power of 2/3 will be y to the power of 5/3. Please tell me that this is right. Or 5/2. Anton said 1. Now I think we're adding 1, which will be 3/3, 5/3. Okay, and then we have to divide. Yes, yeah, no, it's okay. And then I can flip the fraction and I can evaluate from 0 to 8, which 0 will give me 0. Cube root of 8, what is cube root of 8? Cube root of 8 is 2, and then 2 to the power of 5. I'm just trying. cube root of 8 and then to the power of 5. It's, yes, thank you. Thank you, Kieran. It's 32 and times 3. We will need that number. 32 times 3? 96. Yes, okay, I typed the final answer. I was computing this morning, okay? Yeah, but again, we can do this. This is important. Okay, please remember cross-section area and of course the integration. Okay, let's do, I have 2 or 3 more problems because of course I have to add some extra challenge. Yeah, that's always because you are too good. Okay, one challenge is this. When we will get something like that, like a, how do you call, I mean, I typed the name. This is washer, right? When we have like a disc, but when we will have like a hole inside. And now the question is, how can we find the area of these? Let's say this is big R and this is small r because I took from the question. That means how can we find the area just of that washer, of that ring? We have to subtract from the outer, yes, from the big circle, we have to subtract the small one. R, yeah, Jacob said R minus R, but no, we can, we have to play with the areas because subtracting just the radius, we will get that distance. That means this, yeah, this is big R minus the small one, or outer minus the inner, but we still need the area. That means we will need, yes, exactly. Thank you. That means we will need pi r squared, the big one, minus pi r squared, the small one. Yes, thank you. How do you say your name? Kieran? Kieran? Kieran. Okay, thank you. Okay, because I want to say the names. Okay, that means I have this. Yeah, please ignore my X and because that will be, okay, I just call outer and inner, but I think we will use the big R and the small one, small. Okay, that we have to take a big circle and subtract the small one. Okay, that means we okay with that shape. Let's look at the next example. The region R enclosed by the function x and x squared is rotated about the x-axis. Find the volume of the resulting solid. That means what we will need? We will need a function x, which is just the line, okay, and parabola x squared. We know, I mean, we know that because we need, this is like another, like we will need the points of the intersection. Okay, that means we can probably get from the graph, or we can try points of intersection. X squared equals to x. We can subtract x because both of the functions, they have to be equal each other. I can factor out x, and then I have 0 and 1. Okay. And we can see 0 and 1. Okay, that's how we can find. But you will probably, drawing this, you will figure out that 1 squared is 1, and the same value will give you for y equals to x is 1. Okay, but now what we're doing, we can see now we're taking this region and we're rotating about the x-axis. And we're getting something like this. All my points of the intersection, okay, I can keep them. Okay, that's mean now we can see now actually we have similar shape that we did example 1, but we do have like this hole inside because this was nothing. Okay, that's mean now rotating, we just rotating that blue region and we do have a hole. But the same process, we will integrate the cross-sectional area. That means now the first question is, are we integrating in terms of x or in terms of y? Thank you, in terms of x, because you can see this slide, this washer, it's perpendicular to the x. That means we're cutting the x. What are the limits of integration? We're cutting from, yes, from 0 to 1. Perfect. Okay, and now the cross-sectional area is, of course, oh, too fast. It's a washer. Okay, it's a washer, but you see on the graph, I shouldn't include this, but now for the washer, we need to identify the outer radius and the inner radius, okay? I mean, I don't know, this is a little bit tiny, but let me draw here, because the inner radius is this one, okay? We need that radius, the small one. And this is, of course, defined for the certain x between 0 and 1. And the inner radius, what function is touching the inner radius? Which function is involved with the inner? It's the line or the parabola? It's what? X squared. Thank you, it's parabola. That means we can simply, okay, that means this, always the vertical distance is named like a y because it's the distance from 0 up to. Okay, that means this is y, but it's x squared. That's the reason that we call the inner radius x squared. And respectively, the outer radius, maybe I can draw the outer radius here. Okay, we can see it because I don't want to mess up. That means this will be the outer radius. It is y, but it's different y. It's actually, it's the line x. That means the formula, yes, thank you, Heather, it's x. That's when we can see this is the outer. That means, again, this is the challenge, to identify properly inner and outer radius. And then the cross-sectional area is just pi r squared minus pi r squared, outer and inner. X is outer and inner is x squared. Okay, and that's, everything is in terms of x, perfect. And we have to put this to the integral from 0 to 1. This means we will just integrate. I put pi outside, and this is x squared minus x to the power of 4. Okay, x squared and x to the power of 4. Okay. And x cubed over 3, x to the power of 5 over 5. Oh, who can subtract fraction? 1/3 minus 1/5. Common denominator 15, 5 minus 3. Perfect. Yes, thank you, Joshua. You fast. I see some students are working hard. Come on, how many students I see? Do I see only you? Okay, everybody's hiding. Because I don't see like all of the, yes, yeah, thank you for computing, thank you. Good, yeah, good practice. Okay, let's see what else I have. Okay, that means I have 2 more problems. I can tell you, I mean, 2 more questions. Problems doesn't sound good. Yeah. Do you have problems? Yes. The math teachers, they always have problems. Okay. The region are enclosed by, oh, again, x and x squared. That's we just did. But now this region is rotated about the line y equals to 2. Set up the integral which measure the volume of the resulting solid. Set up means that we don't have to calculate. We don't have to evaluate, right? Okay, that's me now. Oh, okay, I have the graph. Maybe I can, okay, I will try to draw it with you. First of all, and then I will erase and show you the graph that I have from your textbook. That's when we do have a function x, and we are a little bit too, because the line y equals to 2 is above. That means let's plan it. Okay, that's function x, that's parabola x squared. We know that is from 0 to 1, and this is also 1. Okay, that's mean now, because the line is not x-axis, I mean the line that we will be rotating about. It's not the x-axis, it's not the y-axis. But the line y equals to 2 is a horizontal line or vertical line? Who can tell me? Of course, I know that everybody. It's a horizontal. That means it's actually here. That means, please, that maybe this will be like a hint. If we're rotating about any horizontal line, which axis is a horizontal line? X-axis, X. That means this, we will follow the same process like rotating about the X. Okay, because when we rotate about the X, we will slice X, we will integrate in terms of X. If we just move the X-axis up or down, it's the same thing in terms of integration. That means since this is horizontal line, X-axis is horizontal, we will integrate in terms of X. That means please remember this. Okay, that means now rotating everything about this axis, we will have, we will like project this above, right? That means we will have 3 and 4, and this will be here, that will be something like that, right? And then that's the rotation. That's the rotation. Oh, I'm not good with but this will be the rotating, because that's the region. I can show you better picture, but just in case if you have to draw it, like we will be rotating. That's, we will kind of have like just the edge, kind of like a really wide coffee cup, but with the hole. I can show you. This one is probably, looks a little bit better, but that's, that's the idea. Okay. Actually, I like my graph, but I will erase. But you know how we get it, how we got it. Okay. That's what we knew that we will be integrating in with respect to X. The same question. Can you tell me the limits of integration? Because we're slicing the X from 0 to 1. Thank you. That's when you understand this part. And you see the pink part is the one of this slice, this slab, and it's of course the washer. Okay, that means it's definitely the washer. And now the thing is, we have to find out the outer radius of that washer and the inner radius, and then we can follow everything. No, I have no, I want you to, okay, that means we know that we have to integrate from 0 to 1 cross-sectional area, which is actually, can I just say washer with respect to X from 0 to 1. And we will need pi r squared. And the only thing that I would like you to get is the outer and the inner radius. Okay, that means now let's see how that line, horizontal line 2, is affecting our radius. Oh, we have the answer, X squared is the outer, but we have to be careful because the line 2, okay, is affecting. That means now this is the center, okay, and okay, we can start with the outer. It's not a problem. That means I will draw the outer. Outer is touching parabola, okay, because that's parabola, and I will, okay, I can draw this, but we're touching. That means what we have, I can even actually, okay, we do have that dot and that dot, the big dots. That's what we have to do. We have to find out that distance, the length of that line segment from the top dot to the bottom dot. And this will be the outer radius. And do you remember how can we find out when we have, I asked you yesterday, like, let's say, I don't know, 7 and 1. What's the distance between 7 and 1? Like, what will be the distance? Heather, I really like this. That's what I was looking for. Of course, 6, but how did we get 6? Top value minus the bottom one. Okay, that means getting back to our graph, we have to identify where, like, what is the height, what is the value of the top dot minus the value of the bottom dot. Okay, that means what is the top one? Top one is just 2. Yes, good. That means this will be 2 minus, and this one is actually x is on this side, but we have to find the corresponding y value. That means this is, let's ignore this one because it's for line. That means this is y, but how this y is defined. That means I can say 2 minus y, but I'm not happy with y. I need the formula in terms of x. What function this dot is touching, parabola or the line? Parabola. That means we just need that y in terms of x. And I believe this y is simply x squared. Yeah, we don't even have to, that means, again, I will try to say, Kieran, I think you were almost right, because you said x squared, but we have to subtract 2 from x. Yeah, I mean 2 minus x squared. Yeah, that we can see this y is just parabola. Oh, we even have this. Okay, that means the outer radius will be 2 minus x squared. Okay, because the function is touching x squared. Okay, and respectively the same, I can, what I can do, let's erase this. You will have this on the video. Let's do the same thing for the inner radius. The inner radius is from here to here, and we're just touching, not parabola, we're touching the line. That means, again, the top value, this is the inner one. It's 2, yes, because it's touching that function, which actually, this is just x. 2 minus y, 2 minus x. Thank you. And dx, I can put pi in front. Oh, not 2, 1. Okay. And we don't have to evaluate. I will just, yeah, I really would like you to have this inner and the outer radius. Okay, that means that's the challenge, to get the outer and the inner radius. And I have this graph, which you can probably, I can erase for now. I can do this. And we can nicely see the outer and the inner. It's actually nice. Yeah, nice graph, because we see. That means, please always remember, to find the vertical distance, we have to find, I mean, the length of the line segment, top value minus the bottom. Do you remember how to find horizontal? Like a length of a horizontal? We have to take the right value minus the left one, and we will always get number of units between, which actually, oh, okay, I typed the, okay. Let's solve this one, and this will be the last question for tonight. We like these functions, the same functions, x and x squared, the region between, the nice loop, but now the rotation is about the line x equals to -1. Okay. Do I have the picture? Oh, I do have it. Shall I? Okay, let me show you. But no. I want you to give me this. Okay. Okay, that's we have the blue part. Okay, we have the line, the rotation line, -1. Okay, that's mean now, of course, I shouldn't show you the picture, but the line x -1 is a horizontal or vertical line? Of course, silly question, because I don't want to say bad word. So instead of silly, also start with the same sound. Okay. Okay, it's all I can say. Rhetorical question. Yeah, do you know what rhetorical question means? That question that we know, yes, the answer is obvious, right? Yeah, we have the same in rhetorical question. Okay, it's a vertical line. That means, do you think we will integrate in terms of x or in terms of y? In terms of header set x, no, y. Okay, because it's the same, like any vertical line will be like respectively the same like because the y-axis is a vertical. That means when we're rotating about the vertical line, we will, because we have to slice it, we have to get that circle or that washer. Okay, that's when we can nicely see. We don't even need, okay, that's we definitely integrating with respect, oh no, hang on, you will tell me the limits. We integrating, and we can nicely see is again a washer. We integrating with respect to y, that's the volume, washer, but can you tell me the limits of integration? Think what we're slicing, of course, because this is one. We're slicing this part, I mean the whole part, of course, but we're slicing the y-axis. Good. Which means from 0 to 1. Excellent. Okay, we will need pi r squared, that's big, pi r squared with respect to y, from 0 to 1. Okay, that's meaning, okay, I cover the radii. Okay, that's we can see this distance represents the outer radius. Okay, this distance, the top one. Okay, so we can see we have that dot and we have this dot, the blue, I mean the big red dots. This one is touching this function. Okay, that's mean what do you think? This the top distance, the top line segment, right? How can you actually, maybe I'm making too complicated, like do you think you know what will be how can we define this length? That because that's the big R. That's the outer radius. We have to identify the right dot minus the left one. Square root of y minus 1. Yeah, I think, because I can say x and -1, right? Because when I project here, I can say it's x, the right value, minus -1. However, we're not happy with x. This is that x defined as a square root of y because it was y. Oh, of course, I can say plus. Okay, that we can see x minus -1, but that x in terms of y is square root of y. Okay, that means that's correct. Let me uncover this. Perfect. And who can give me the small radius, the inner radius? This one is the big one. I'm covering. That means now I can use different color from blue dot to the other blue dot. And now we touching, it's also X, but it's defined differently. That means who can give me the small radius? It's, I can still say X minus 1, right value minus the left value, just to be, but that X is simply, okay, Y plus 1. Oh yeah, it's X plus 1, but we need in terms of, it is, because we can even see it's X plus 1. X units to the right, 1 unit to the left, X plus 1, but this is the straight line, which means that X is defined as a Y. Good. I will uncover this, and that's the small one. Okay, that means we can say volume is defined as an integral from 0 to 1, square root of y minus 1, oh no, plus 1, minus y plus 1, dy. This is big one, this is the small one, outer and inner. Okay, and I believe that's my last question. Yeah, that's when we can see the concept is so short, but we did quite a lot. You can probably check, I think, okay, I do have a video, but what's actually probably this is the good news for you, because previously we have to cover another section, 5.3. But for some reason, the math department and all of us, like teaching calculus, we decided not to cover 5.3. But I have nice video which actually connects these two sections. But you can probably tomorrow, like in the afternoon, I can put a new video with additional question just from this section, 5.2. Okay, because this is the summary, but but we will not cover this. This is also a nice section, but we have just 5.2. Let me come back. This is actually the nice summary. Okay, we will use the disk formula or the washer, the disk method or the washer method only. Okay, that means we can see we can only integrate. Yeah, I mean with respect to x or with respect to y, depends. Okay, and that's the volume. Or we can integrate cross-sectional area with respect to x or with respect to y. Okay, that's the only thing. Actually, if you do you think we can answer this question? Because you see, that's the thing, we have to because actually this is 5.3. I have to. Okay, I have to change that because we always have section 5.2 and 5.3. This is the first semester that we're not covering. Okay, I will double check. I'm assuming, I mean, your weekly questions are definitely correct. Probably some sample questions will be will include 5.3. Okay, that means definitely I believe that's not the option. Let's find the correct answer. Okay, because I think we can try. Yeah, do you think we can stay, I don't know, a few more minutes? Yeah, yes, okay, let's solve it. I'm just, okay, I can tell you that this will be not an option. Okay, because it's 2 pi, it's different, it's from the other section. That means just disk and washer method, no other methods. Okay, set up an integral for the volume of the solid obtained by rotating the region bounded by square root of x minus 1 and y equals to x minus 1 about the x-axis. Okay, that means we will have, since we rotating about the x, we integrating about the x. That means that's not a problem. Everything is in terms of x. That means we good. But we have to find out the correct. You may probably guess, since 2 functions are given, we will have the washer. Yeah, that's how we can identify, because we will have outer and inner radius. I mean, one function and the other function. what we can do, let's draw the functions. Square root of x minus 1, we have to shift to the 1, right? That will be square root of x minus 1 to the right, because x minus 1, when I substitute 1, that's the x-intercept. The line x minus 1 is just the straight line with the y-intercept -1. Oh, I think that's the line. Yeah, makes sense. Okay, that we do have a point of intersection. We have to find out that point. Okay, I don't know this point, but this is square root of x minus 1, and this one is the line x minus 1. Point of intersection, x square root of x minus 1. Or if we like, because I mean, we can still solve it, but it's quite, we have to square both sides. It's quadratic equation. Do you think we can make educated guess? What value of x, like even looking at this, what value of x will give me the right and the left hand side the same? Or it's too complicated. 2, when we substitute 2 minus 2, yeah, I think so. It's 1, square root of 1, 1. Yeah, okay, that means I think it must be 2, because it's just one point of intersection, no other points. Yeah, that means instead of like solving the quadratic equation, we can do this. And actually, I just eliminate B and D, okay, because you will not see these options. And each of the options has the limits from 1 to 2. Okay, that means what we're doing, we're rotating. I don't know if we would like to see the solid. Okay, that means we will be rotating about the x-axis. That means we slicing x-axis. Okay, that means this is that's my solid. I can draw it. Okay, but I can just write this will be my inner radius. This will be my outer radius. Okay, that means I will washer pi r squared minus pi r squared. And in terms of x, volume. And you okay with the limits of integration from 1 to 2? Okay, because because we will be, since rotation is, I will be like slicing, I will remove this. Always think like what we slicing, then we will never make the mistake. Oh, great, I erase my curve. Okay. Okay, that's me now, outer radius and the inner radius. Who can tell me what is this one is easy. We don't have additional lines. We're not shifting 1, 2 units up or down or left or right. Radius, the inner radius is touching the line. That means what is the inner radius? Of course, it's simply x minus 1. And what is the outer radius? It's touching the root function. Yeah, because it's no problem. Everything is in terms of x. Always when it's in terms of x, we're simply taking the formula for the function. Yeah, because that's the y, the vertical, both of the vertical distances. That means this is y and this is also y. That means we have y minus 0, y minus 0. That's mean, but we have different y's, different formula of the function. Okay, that means which answer is correct? Is the E or A? We have to be careful. Oh, E is tricky. Yes, because we have to, A will be the correct answer. We have to, we can't square like, we can't combine the squares. No, that's not the same. We have to square one radius, another radius, and then pi. Okay. That means, yeah, you can expect question like that, but of course option B and D will be different. Probably I will set up an integral in terms of y to make your life a little bit harder. Yeah, just because that's what we have to know. Yeah, if we integrate it in terms of y or in terms of x, but you know, you will get correct. Okay, no more talking. Thank you very much for all of your answers, for the great participation and staying with me so late. Thank you. I really enjoy, and even looking at some of the students. You can put the cameras on. Thank you for the students who put the camera on. Okay. Oh, yes. Hi, Heather. Okay, it's so nice. Yeah, probably we have to set up some session once that maybe you can talk. Then I can hear you. You hearing my beautiful accent. Okay. Thank you very much, and please work on your discussion, on your problems, on your web assign, and you will hear from me next week. Yeah, I will watch you on the discussion. Thank you. Oh, thank you, Heather. You're so nice.